Hi, my name is Alexander Sobol, and today I would like to present you our recent article on scalar perturbations from inflation in the presence of gauge fields, which we did in collaboration with Ruth Dürer and Diepengarg from Geneva, Richard von Eckerstein and Kai Schmidt from Münster, Stanislav Wilczynski from Geneva, and Taras Shevchenko National University of Kyiv. Our article is now available online on arXiv via this link, and also it is submitted to Physical Review D. And today I would like to briefly discuss the main ideas behind it. So as many people believe, inflation is one of the most successful paradigms that allows to solve the long-standing problems of the standard cosmological scenarios, such as horizon problem, flatness problem, monopole problem, and so on. And in its simplest setup, it is realized by the single scalar, real scalar field called inflaton, which is slowly rolling along the slope of its very flat potential, and has equation of state which is very close to the vacuum, omega equals to -1. And because of that, the universe exponents very fastly, quasi-exponentially, and quickly becomes very cold, empty, isotropic, and flat. But also, it is very famous for generating the perturbations on top of this space, homogeneous and isotropic space-time, because these perturbations act as initial conditions for further evolution and then give rise to CMB anisotropies, to the large-scale structure of the universe, to stochastic gravitational wave background. And also, if the scalar perturbations are strong enough, they may produce later the primordial black holes, which also strongly impact the stochastic gravitational wave background, the large-scale structure, but also can act as dark matter, at least a part of it. So studying inflation is very important, as it has a rich and interesting phenomenology, but it becomes even more interesting if the gauge fields are present during inflation. So if we produce gauge fields, it leads to much more interesting phenomena, such as fermion production via the Schwinger effect, for example, or effective universe reheating after inflation, which starts even during in the final stage of inflation. For example, if the gauge fields are helical, then during the electroweak phase transition, this may lead to the generation of baryon asymmetry of the universe due to the chiral anomaly. Moreover, the gauge fields produced during inflation may be preserved until now in cosmic voids and may explain the presence of magnetic field in voids, which is inferred from the observations of distant lasers. So in the presence of gauge fields, the phenomenology becomes much more interesting, but also much more complicated, because now the gauge field, as an important player in the field, it also starts contributing to tensor and scalar perturbations. And it may spoil the very nice predictions of inflation. So it is very important to keep track of everything, in particular, to keep track the presence of gauge fields when computing scalar perturbations, tensor perturbations, because it can strongly alter the predictions of the whole model. And the aim of this work is indeed to take into account self-consistently the presence of gauge fields during inflation, also with the possibility of its backreaction on the inflaton evolution, because if the gauge field is strong enough, it can also change the evolution of the inflaton, the expansion rate of the universe, and all this is then reflected in the spectrum of scalar perturbations. And we would like to do this self-consistently in the leading order, in the first order perturbation theory, but including all contributions to the scalar perturbations coming from the inflaton, metric, and gauge field. Okay, so we take a rather general model of inflation with in the presence of Abelian-gauge-field, which includes the kinetic coupling and axial coupling between the inflaton and gauge field. So the kinetic coupling is given by the function I1 of phi, which multiplies the usual kinetic term of the gauge field, and axial coupling multiplies the f mu tilde, which in the absence of this function would be just the boundary term, so it would not impact the equations of motion. Introduction of these interactions is very important because in the absence of those, the gauge field action would be conformally invariant. And since the Friedman universe is conformally flat, then there would be no generation of gauge field. Yeah, so it would be not enough to produce some strong gauge field which could then impact the perturbations. Okay, so this is pretty much general model because in the literature both of them separately are widely used. So we decided to do the general computation. And more explicitly, if we highlight in green everything which depends on metric, in blue everything which depends on the inflaton, and in red everything which is gauge field, you can see from here that all three components are coupled to each other, so they cannot be separated. So it is very important to perform the self-consistent treatment of all three ingredients. So since we are going to study perturbations, we have to discuss perturbations on top of what we are talking about. So first, homogeneous and isotropic background. It is described by the specially flat Friedman Lemaitre-Robertson-Walker spacetime with this metric in conformal time. Yes, then we have the classical only time dependent, not coordinate dependent inflaton field, which we denote by phi with index c, which means classical, and also the gauge field. Of course, it is a quantum field. It is x dependent, but its vacuum expectation values, such as e squared, b squared, e dot b, they are assumed to be only time dependent, not coordinate dependent, and only those vacuum expectation values are expected to drive inflation, to modify the Hubble rate, to backreact on the inflaton, on the classical inflaton evolution. So in total, all these three ingredients are homogeneous and isotropic. And they are described by the following system equations of motion. Of course, from Einstein equations, we obtain the Friedman equation, which determines the Hubble rate. So how quickly our universe is expanding. And you see in this Hubble rate, we have the inflaton contribution, but also the gauge field contribution. Also the Klein-Gordon equation, which describes our scalar field evolution. And also on the right-hand side, we see the terms which are coming from gauge field. And for gauge field itself, we have to write Maxwell's equations, but since they enter our equations of motion only in the form of such vacuum expectation values, it is also convenient to write down equations of motion for e squared, b squared, e dot b, and so on. And this is the so-called gradient expansion formalism, which was developed by some of us previously. So this is basically the total system of equations which describes the background evolution. And what is important that even at this stage, we already take into account the gauge field as on the same footing with inflaton. Yeah, so this is not some small perturbation. This is the factor of the same importance, and this allows to keep track of gauge field backreaction. And this was our main goal in this article, to develop formalism which works also in the strong backreaction regime. Okay, then on top of this background, we consider perturbation. So metric is perturbed like that. So we introduce the Bardeen potential, or we use the conformal Newtonian gauge where the metric perturbation is just parameterized by two functions, psi and phi. Then inflaton is perturbed by some delta phi. And for the gauge field, it is very simple because it is already x-dependent, as we said. So we are considering the classical homogeneous part, which is just expectation value, plus some perturbation, so that in total they just give the electric or magnetic field. Yeah, so this is how we define our gauge field perturbation. And in this sense, our gauge field is considered as a quantity of the half order, not the first order, half order, because only the quadratic combinations then are considered as the first order perturbation. And for those quantities, psi, phi, delta phi, and all kinds of deltas, we can write down Einstein equations, Klein-Gordon equations, Maxwell's equations, and they govern the joint evolution of all these quantities. And you can find the full version of those equations in our article. But it is convenient to use the gauge invariant Mukhanov-Sasaki variable, which is a combination of all three ingredients which we have in our problem. So its gauge invariant definition is like that, and if we, so this V velocity potential is extracted from zero I component of the energy momentum perturbation, and we have such combination. So now what is new in the present paper, that typically people consider only two components, the metric and inflaton. Moreover, in the presence of gauge field, there is a claim, very strong claim, that metric perturbations are not important. Therefore, zeta is just linearly related by some coefficient with the delta phi, with the inflaton perturbation. And in this article, we would like to consistently take into account all three terms. And why this zeta is very convenient, because it is gauge invariant. So we can define it. We chose the conformal Newtonian gauge, but we could work on any other gauge, and zeta is gauge invariant. And the second, in the absence of gauge field, this variable becomes constant. It freezes on superhorizon scale. And it was very convenient because we can compute this zeta for the mode until it crosses the horizon, and then it is frozen, and it has the same value when it re-enters the horizon later during radiation domination. Unfortunately, now this is not the case in the presence of gauge field. So if we compute zeta dot, we will see that it doesn't vanish on superhorizon scale. And therefore, in order to obtain the scalar perturbation on the radiation domination, when the mode re-enters the horizon, we would need to do some matching. Yeah, so this is not just a very simple relation that it is the same value. So we would like to study this aspect also, but we postpone it for future studies. Okay, so for this zeta, taking all these Einstein, Klein-Gordon, and Maxwell equations and just performing some algebra, we can write down equation in such form. So this is the second order differential equation for zeta, for the Fourier mode zeta, with some coefficients. And it has a source, and this source depends only on the gauge field. And what is important, I would like to emphasize once more that this P and Q, they depend on the background inflaton, on the background scale factor, and on the background values of E squared, B squared, E dot B, and so on. And thus, they take into account the possible backreaction of the gauge field. Also, this term, the source term Sk, it contains all possible contributions. So it was consistently derived from the full Einstein equation and Klein-Gordon equation. It means that we do not neglect terms in the which are of the first order in perturbation theory. So this is the full expression. And as usual, we can write the formal solution to that equation. Zeta is some zeta 0, which is the solution for homogeneous equation, and it is interpreted as some vacuum fluctuation. So this zeta is considered as a quantum field. So this is vacuum fluctuation of this quantum field, and this is the source or inverse decay contribution, which is sourced by the presence of gauge fields. And since they include the annihilation creation operators of different kinds, they are statistically independent. So when we compute different kinds of correlators, these two terms appear to be fully statistically independent. So having this formal solution, we can now determine some observables such as power spectrum, scalar power spectrum, very important observable. And as we discussed, because of these two independent contributions, we have two also terms in the scalar power spectrum, the one which comes from vacuum fluctuations. And this is the full analog of usual vacuum scalar power spectrum from inflation. But now it may be modified by the presence of gauge field because of backreaction. So already this part may be non-trivial in the presence of gauge field. But of course, the second term, inverse decay, is fully determined by the presence of gauge field. And in some cases, it can be even more important than the first term. Okay, but also the scalar bispectrum. In the leading order perturbation theory, the bispectrum for pure inflation without any gauge field just vanishes. So it appears in higher orders. But now we have the term which is already quadratic in annihilation creation operators, and it leads to non-Gaussianities. Therefore, even at the first order, we already have some non-trivial bispectrum. And expressions for the scalar power spectrum and bispectrum are also present in our article. I do not show them here because they are rather cumbersome, but you may see it in the article. Okay, and now we would like to test our formalism in some simple case. And one of the simplest and well-known cases is the axial inflation without backreaction. It was extensively studied analytically in 10 years or so ago by Barnaby, Peloso, and co-authors in several articles, and they got very interesting and important results. And they had the following assumption. So no gauge field backreaction on the background evolution, first of all. So we just treat the Friedman and Klein-Gordon equations as the gauge fields are absent. Okay, so we take the simple setup where the Hubble rate in physical coordinates, the physical Hubble rate is constant. So this is just the theta basically. And the gauge field production parameter, which is just the inflaton velocity, rescaled inflaton velocity, is also constant. In this case, the gauge field mode functions are known analytically. They are expressed in terms of Whittaker functions, and there are also some convenient approximations for those functions, so that even the power spectrum and bispectrum, they can be computed analytically with some approximation. And another assumption is that there is no metric perturbation. As I said, that zeta is just linearly related to delta phi, to the inflaton perturbation, and the metric perturbations are flow roll suppressed. As we will see from our study, this flow roll suppression is not obvious, because if something is flow roll suppressed, this means that this is a universal property. This means that for any values of parameters, for example, of this psi parameter, we should obtain that indeed the impact of these metric perturbations is negligibly small. As I will show later, this is not the case. And therefore, I put the question mark here. So the question of whether the metric perturbations are slow roll suppressed or not is not clear for now. And for example, future studies of the strong backreaction regime, which we are going to perform in future, I hope will help to answer this question. Okay, so for the scalar power spectrum and scalar bispectrum, they obtain the following expressions. So the power spectrum, the induced power spectrum is parameterized by some function f2 of psi, and the bispectrum is parameterized by some function f3 of psi, and the simple approximate estimate for those functions is like that. So this is some power law functions of psi times some numbers, some small numbers. And so that was the old result. And this is the reference point for our study. And concerning our new result, so as we discussed, now there is no backreaction on the background evolution. Therefore, the coefficients P and Q in our equation for zeta are just the same equations as in conventional inflation. So this is like Mukhanov-Sasaki equation. However, what is different is the source term. So for the work of Barnaby and co-authors, the source term is just given by this. So this is basically the product, scalar product E dot B is what sources our scalar perturbation. In our work, the source term is much more complicated. So we see some counterpart of this here. So there is indeed some EB, but the operator is not the scalar product. It is Ki, Kj over K squared. And also there are contributions from E squared, B squared, and more complicated things. Yeah, so this is the difference already on analytical level for the source term. And then we performed the numerical simulation. So by solving, so by taking this source, we computed the power spectrum and bispectrum. And here I would like to show the result. So here, the black solid line represents our main result of the work. The blue result is the power spectrum computed with this simple source term, but treating the mode functions of the gauge field exactly. So we took the expressions in terms of Whittaker functions, plugged into our correlators, and computed everything numerically. So these basically, by comparing these two lines, we compare apples to apples, because everything else except for the form of the source term is the same. And this orange line is representing the simple analytical estimate which was done, which I showed previously. Yeah, so this is, we just multiplied by psi to the 6th to cancel the power law. And this orange line corresponds to that constant value. So we see that they are pretty close. The results are pretty close for large values of psi parameter. So starting from 2 or 3, the two lines are almost indistinguishable. However, for smaller values of psi, there is some difference between them. And it is some maybe 10–15% difference. And therefore, we cannot say that this is slow roll suppressed, because the impact of metric perturbation is slow roll suppressed, because now in this simple setup, the slow roll parameter is just 0. So we are considering that our H is just constant. So the flow parameter is 0, but we have already non-zero difference between them. Also, I would like to say a few words about these bands. So if we plug the exact mode functions, the Whittaker functions in our integral for the power spectrum and also for the bispectrum, we see that it is divergent. It is very natural because in quantum, we are considering loop diagrams in quantum field theory, and they are naturally divergent. And the correct way of dealing with this would be to do some renormalization procedure to extract some divergent contribution and so on. But the expressions are very complicated, and as a first approximation, we decided to do the regularization by other, but also very common method in this literature, just by cutting the momentum integral at some value, at some UV cutoff. And this UV cutoff separates the modes of the gauge field, which are enhanced by tachyonic instability due to this axial coupling, from modes which are not enhanced, which behave like vacuum fluctuations. Motivation is very clear. Since the mode is tachyonically enhanced, then it is much larger than the vacuum value that would be without this gauge field to inflaton coupling. And if we will subtract some vacuum contribution when performing this QFT regularization, then it would be almost not affected, because it is already much larger than the vacuum. And for those modes which are still inside this horizon, which behave like vacuum fluctuations, this subtraction would cancel almost everything. So this is more or less natural to cut our momentum integral at this threshold momentum for which the mode starts experiencing this tachyonic instability. And this corresponds to solid lines. However, since this is just hand wavy explanation, and why should we take exactly this momentum? We can vary it, take it a bit larger, a bit smaller. We decided to vary this UV cutoff by a factor of 3, larger or smaller, so that in total the variation is by an order of magnitude. And we see that for large values of psi it is not important, but for small values of psi it makes a very strong impact on the result. So basically the gray band corresponds to smashing of this solid black line, and the light blue band corresponds to this blue dashed line. Yeah, so in principle, if we take into account seriously this theoretical uncertainty, then within these bands of uncertainty, the two results are in agreement between each other. However, if we do the same regularization, the same cutoff for different schemes, the results of these lines within these bands would differ by 10–15%. And qualitatively, the same picture also is valid for F3 function, which parameterizes the bispectrum. So this is equilateral configuration of bispectrum, but when all three momenta of zeta in correlator, they are equal by the absolute value. And we see exactly the same. So for large values of psi, the two approaches, the old one and the new one, they give the same result. And for smaller values, there is a difference of the same order. And also we have a large uncertainty band due to the choice of the ultraviolet cutoff. And the question with the ultraviolet cutoff, of course, requires a more rigorous, mathematically rigorous analysis where one can perform the conventional regularization technique to extract the finite contribution. And this question is also very interesting for us. We are planning to address it in the future studies. Also, we computed the non-equilateral power spectrum, and it is parameterized by the so-called shape function. So it describes how the bispectrum for non-equal momenta is related to equilateral bispectrum. It is normalized in such a way that for equilateral configuration, where these x2 and x3 equal to 1, it is just 1. And we see that for different values of psi, the shape function slightly changes, but it remains peaked on the equilateral configuration. Yeah, so this is mostly equilateral bispectrum. So to conclude, in our recent article, we studied how the Abelian-gauge-field production during inflation affects scalar perturbation. In the case when the gauge field interacts with inflaton directly by some kinetic and axial couplings and via gravity. And in our new approach, we consistently work in the first order perturbation theory. We include scalar perturbations of all types which are present in our system. So from metric, inflaton, and from gauge field. And our approach allows one to take into account the gauge field backreaction of the background evolution. And in the simple case, which we just used as a reference, just to compare our new results with something which is well known, which is axion inflation without backreaction, we observe that the effect of including metric perturbations is small for values of the gauge field production parameter larger than psi equals 3 or even 2. And this is in agreement with the previous results in the literature. But in the region of small psi parameters, and our new results are slightly different from that well-known result. And also we expect that larger differences may be present in the strong backreaction regime, because here in this very simple model, we are considering just ideal situation with de Sitter space-time with constant gauge field production parameter. But in real situation, we know that in the strong backreaction regime, the evolution of this psi parameter is non-monotonic. It is very complicated. Also everything, also the inflaton, it sometimes even moves non-monotonically. It can stop, it can even slightly go back the slope of its potential. So it is very interesting to study also this gauge field production and production of scalar perturbations in the case of strong backreaction regime. And we are planning to do this in our future studies. So for more technical details for all analytical expressions and results, please see our article on arXiv and stay tuned. Thank you for your attention.